All right, let's dive into a data structure that sounds way more complex than it actually is, the monotonic stack. Seriously, it's a powerhouse, a super clever tool that can elegantly solve a whole bunch of tricky coding problems. And by the end of this, you're going to know exactly how to use it.
So, let's kick things off with a question you've probably seen in a coding interview. You get a list of numbers, right? And for each number, you have to find the very first number to its right that's bigger. How do you do it? And more importantly, how do you do it fast?
Now, the first thing that probably pops into your head is what we call the brute force method. You just take each number, and then you loop through everything after it to find a bigger one. Easy enough, right? Well, it's a trap. As soon as your list gets big, those nested loops will slow your code down to a crawl. There has to be a better way.
And of course, there is. This is where our hero of the day makes its grand entrance, the monotonic stack. This is the elegant solution. It's a clever data structure that lets us solve this exact problem and a ton of others like it in just a single pass. Let me show you how. So, what is it really? At its heart, a monotonic stack is just a regular stack, but with one special rule. The elements inside have to stay in a specific order, either always increasing or always decreasing. The magic isn't in pre-sorting, though. The magic happens when we add something new. If a new element is about to break the rule, the stack actively kicks out or pops whatever's in the way until the order is restored.
You've basically got two main flavors. You've got your monotonic increasing stack, where numbers get bigger as you go up. This is perfect for finding the next smaller element. And then you have the monotonic decreasing stack, which is the opposite. Numbers get smaller as you go up. And you guessed it, that's what we use for finding the next greater element, just like in our problem.
This quote right here is the golden rule. It really is that simple. Before you push a new number onto the stack, you take a peek at the top. If your new number breaks the sorted order, you just pop elements off until the order is fixed. Then, and only then, do you push your new number. That's the whole game.
Okay, theory is one thing, but seeing it work is where it really clicks. So let's walk through our next greater element problem step by step with a real example. Pay close attention, this is where the magic happens.
All right, here's our setup. Our input array is 2, 1, 4, 3. We've got an empty stack, and here's a super important detail. We're going to store the indices of the numbers in the stack, not the numbers themselves. You'll see why in a second. We also have our result array, all filled with -1s for now.
Let's get started. First up is the number 2. The stack's empty, so we just push its index, which is 0. Simple. Next is the number 1. We look at the top of the stack, which is index 0, representing the value 2. Is our new value, 1, smaller than 2? Yep. So our decreasing order is maintained. We can just go ahead and push index 1 onto the stack.
So after those first two numbers, our stack holds the indices 0, 1. And if you look at the values they represent, 2, 1, you can see they're in a nice decreasing order from bottom to top. Perfect. The result array is still empty.
And here we go. This is the key moment. We're about to process the number 4. This is where that popping logic we talked about really comes alive.
Okay, so we're looking at 4. We peek at the top of our stack. The index is 1, which represents the value 1. Is 4 bigger than 1? Absolutely. This means 4 is the next greater element for 1. So we pop index 1 and we set result 1 equal to 4. But wait, we're not done. We look at the new top of the stack, index 0, which is the value 2. Is 4 bigger than 2? Yes again. So 4 is also the next greater element for 2. We pop index 0 and set result 0 to 4. Now the stack is empty, and we can finally push the index for 4, which is 2.
And just look at that. In one fell swoop, we found the answer for 2 different numbers. Our stack now just has index 2 in it, and our result array is already half full. See how much faster that is? No rescanning necessary. Almost there. Let's finish this up by processing the very last number in our array, the number 3. We're just going to apply the exact same logic.
We look at our new number 3 and compare it to the top of the stack. That's index 2, which holds the value 4. Is 3 smaller than 4? Yes, it is. Our decreasing order is safe, so we simply push the index for 3 onto the stack. And with that, we've hit the end of the array. Our final result is 4, 4, -1, -1. The indices still left in the stack, for numbers 4 and 3, never found a greater element to their right, so their values in the result array stay as -1.
Done. So you might be thinking, okay, that's a cool trick for that one specific problem. But the real beauty here is that this isn't a one-off trick. It's a powerful, reusable pattern. Once you see it, you start seeing it everywhere.
I mean, just look at this list. Finding stock prices, daily temperatures, the famous largest rectangle in a histogram problem, trapping rainwater. All these problems that look totally different on the surface can be solved efficiently with this one simple pattern.
So why bother with all this? Why not just use those simple nested loops we talked about at the beginning? Well, as it so often is in programming, the answer is all about performance.
The monotonic stack gets us a time complexity of O of n, which means linear time. That is a huge upgrade from the O of n squared of the brute force way. And why is it O of n? Think about it. Every number in our list gets pushed onto the stack exactly once and popped at most once. We process the entire list in one go. That is a massive, massive win.
So here's the real key insight. This is what you should take away. You want to have a little light bulb go off in your head when you see a problem asking for the next greater or previous smaller element. If you find yourself needing to compare elements in a range and you know nested loops are just too slow, the monotonic stack should be the first tool you reach for.
We've seen how just one simple rule, maintaining order in a stack, can unlock these incredibly powerful and fast solutions. So I'll just leave you with this to think about. Now that you